Have you ever wondered if dangerous adversarial examples are part of the diffusion model's learned manifold? Hi, I'm Peter, and together with my colleague Ricardo Ral and Janis Kuiper, my advisor, we will explore this question and fascinating world of robustness of generative diffusion models. Are adversarial examples part of the learned manifold? First of all, what are adversarial examples? Adversarial examples are minimal imperceptible perturbations. They are usually on the input data and they change the classifier prediction. A model is not adversarial robust if it is fooled by adversarial examples. On the other hand, banning data refers to the data points that are considered normal. Diffusion models have drawn significant attention for the success in approximating data distribution, yielding state-of-the-art generative results. Diffusion models are usually used as foundation models. Foundation models, as shown here, are huge models trained on a huge amount of data. And then these models are fine-tuned or adapted to subtasks where they show really high performance. We want to know if we have attacked data, transform it through the diffusion model, does it differ from Bannon data? If yes, then there is compelling evidence that these diffusion models, that these adversarial examples do not belong to the learned manifold of the diffusion models. One must be said that foundation models are a single point of failure because how it's used nowadays, and it's very important to check and explore the adversarial robustness of these models. Our contribution can be summarized as follows. First of all, we show a tool to check if adversarial examples are part of the diffusion model's learned manifold. Then we think that by our knowledge that we pioneer adversarial sample detection by the pixel size of the images, which is over 512 pixels. Before that, there were only detection results on smaller image sizes. Next, we want to know if there are fingerprints after the transformation. Besides adversarial examples, they are not only generated by only one attack method. There are different attack methods which generate different type of adversarial examples, and we want to know if we can distinguish between them. Lastly, we show an ablation study on the transferability of the detector by assessing its performance. This is very important because the strength of adversarial examples itself is that they can be generated on data sets or models, and then they transfer very well to unknown data sets and models. And we want to know if we can stop them. Here is a high-level overview of our method. On the left-hand side, we can see the inversion, the Gaussian noise, and the reversion process, which is the standard procedure of the diffusion models architecture. Then as input, we have two data distributions. One is the adversarial and the other one is the benign distribution. Here we just show two data points, and XA is the attack counterpart of XB, and you see there's a bit of difference because of the minimal perturbations of the adversarial examples. Then this inversion, Gaussian, and reversion shows the transformation through the diffusion model, and afterwards as output we get again the images and the image is now transformed, and there's a larger gap between the tagged counterparts and the binary ones. And we want to know if there's really a pattern or something we can learn, grasp, so that we can answer the question. There's an evidence that adversarial example do not belong to the trained manifolds of the diffusion model. On the right-hand side, just show an overview of the algorithm of the training. We use an off-the-shelf ResNet 50 model to train based on this transformed data. So to the experiment setup, we have the data binary and detect images, adversarial examples. Then we have the pre-trained DDIM weight, and from the image net and for the image and Cyber 10, we downloaded this pre-trained weights from OpenAI GitHub repositories and just use them. For the transformation, we use the DDIM inversion reversion step. And the DDIM architecture is very useful because it's deterministic. And since we use as initialization the input image, we always generate the same output image. And lastly, we have a binary or a multi-level detector, and class 0, 1 is the detect image, and class 0 is the binary image. Here on the right side, we have just the data, then they're transformed separately and then trained on the classifier. Here are some transformed examples. In the first column, you can see the original image. In the second column, the B9, and in the rest, the adversarial attacks, usually global attacks, except the masked BGD, which attacks just one part of the image. In the first row, we have an image of a door of a very old building. And it's very interesting that here the binary samples are very smooth, but the other samples, you can see tiny patterns in the image. And even in the masked BGD, we can see the rainbow colors of where the patch was, which was not removed by the transformation. And there's even a face out of the door. Yeah. On the second row, you can see there's a lock, and even there are missing parts of the lock after the transformation. And it's very interesting at the auto attack, there's some jitter, and must be these times the patch, the rainbow color of the patch is removed. I don't know exactly where is the patch on the transformed, or where was the patch on the original attacked image. Let's put it in some numbers. Here are some detection results on the Cyber 10 dataset, which is usually the standard dataset for adversarial training, the standard method to robustify classifiers, model classifiers. We have here two attacks, auto attack and BGD. They're very similar, and in the community it's discussed which one should be used. Comparing defenses are very difficult because it depends on the focus, and there are different types of defense methods. We listed there adversarial training, input purification, supervised learning, and which usually use auxiliary networks. Supervised learning methods usually proof of concept to grasp the attack pattern, and we also can show that with our method, which is supervised, has an accuracy of 95% and higher. And but it's just a proof of concept, and auxiliary networks can also circumvent by attackers. Input purification is also very interesting because there are diffusion models used to purify the input, which shows an accuracy close to 90% on the standard accuracy and 70% on the robust accuracy. Why is Cyberden a standard data set for the robust for the adversarial training? Because of the computational expensiveness of this method. Now we want to know on higher image sizes, on higher image resolutions, if the images, if the detector becomes better or worse. Cyberden is a very simple data set. Let's switch to ImageNet, which has 1,000 classes and is more complex and has 224 pixels. And here we can see that we have gained accuracy over 99% of both attack methods. And this is really, improvement. The impact of the diffusion reverse steps, generating a sample for diffusion models can be very expensive. By default, there are 1,000 steps, and this steps could be saved, and this sample generation would be faster. This is what we would aim. And we can clearly see when we would save steps, then we would lose in accuracy. But if we double the steps, we can see a minimal improvement in accuracy. But is it worth actually to do that? And the true negative rate and the false positive rate are inversely proportional. Okay, increase again the image resolution. Now we want to know if our image size on 512 and 512 is also very effective. And our method shows an accuracy over 90–70%, and which is even an increase of 4% over the standard ImageNet size. And we think, that the detection tends to increase with higher resolution. Although usually attack methods could be more effective on higher resolution images. And we think, by the best of our knowledge, we are the first to show detection results on 512 pixels. Then here we just outline the performance on various attacks on different epsilon sizes, and on the white box attacks, we can see that the accuracy is almost every time over 90%, except Kali and Wagner attack. And it's interesting to see the novel attack TIFF attack, which utilizes a diffusion model to attack images. We have over 99% accuracy, close to 100. This might be the reason because TIFF attack also uses this DDIM pre-trained weights as we use through the transformation. On black box attacks, we also have an accuracy over 90%. Just to show on more attack methods the efficiency of our detector. Here are some fingerprint, so identification. On the left hand side, we have a confusion matrix on the white box attacks, and we can see that there are clear fingerprints, except for PGD and out attack, which are again very similar attack methods, and default and Calvini and Wang attack, they're also sometimes mistaken. On the right hand side, in contrast, we have the black box attacks, and here the fingerprints are very clear, and they're not really mistaken. So to the question to transferability, the transformed data, so the attack data does not transfer well to unknown attacks. This is our conclusion. In our experiment, we trained a binary classifier augmenting with white box attacks using the smallest epsilon size and also the deep full and Calvini and Wang attack. We can see that yes, the augmentation of training data helped a bit when it's the same attack method, but with larger epsilon sizes. But for unknown attacks, this attack method is not successful. This defense method is not successful, and this should be our fault, and still shows the strength of the adversarial attacks. Our conclusion is that our method unveils compelling evidence suggesting that adversarial examples do not belong to the learned manifold. We think that it's a reliable tool for uncovering adversarial examples and also to show the fingerprints. We do not claim this method as an adversarial example defense because it's just supervised learning method and it cannot adapt during test time because the attacker could learn and could do more tricky attack methods. If there are any questions, I'm happy to answer them. Please don't hesitate to write me an email. I'm looking forward to hearing from you. Thank you for your attention and goodbye.